I'd like to introduce our first speaker of the day. Zachary Lipton is professor of machine learning in the School of Computer Science and the Taft School of Business at University. He is also the director of the ACMI, Approximately Correct Machine Learning, Machine Intelligence Lab at CMU. He specializes in deep learning, foundations of data-driven decision-making and robust prediction, applications to healthcare, and critical concerns surrounding ML's impact on society.
Hey, can you hear me? All right, cool. Yeah, thanks for having me here. Thanks, Peter and Mel and everyone for organizing. Can't you hear me? Should I just speak louder? I'm from New York. I could do that. All right, you can all hear me now? All right. Is that cool? Or is that a problem for the stream?
I think the stream's working. It might be showing presenter view of the stream.
But I mean, can you hear me?
That's not something I know how to switch.
Oh, it's on. Oh,
that's good.
Okay.
Do you want to switch it to the full screen view?
But
It's okay. It's fine.
Or it's streaming like that?
Oh, streaming like that. Yeah, I do know how it's sharing the wrong. Well, do you have Zoom?
It's in a restream. It's just sharing the whole screen.
Or how do you go to? Where's Zoom?
Can you? It's not in Zoom. Is there a way
Oh.
to just have it so it's showing the screen outside of presenter view?
Oh, so it's just not showing presenter view at all?
Yeah, so it's like just full screen. Do you know how to
Sure,
do that? Now, do you know how to change it out of presenter view?
Yeah, I don't need a presenter view.
Because it could
Display setting?
just to have the whole screen as the slide instead of having it like this. That's perfect. Yeah.
All right, cool. All right, it's taken away my presenter view. I didn't actually have any notes, but if I fumble anything, let's just pretend that's the reason why. Cool. So I kind of wanted to take the opportunity here not to. I'll touch a little bit on my research, but or something close to my research, but I wanted to paint maybe a slightly broader picture of. I guess we're here talking about conceptual things about deep learning and AI and how advances in AI might bear on certain kinds of questions about having machine intelligence systems that understand language, that have certain kinds of moral standing, all these sorts of questions. And I think it's worth stepping back and sort of making sure that we're all on the same page about what do we even mean by deep learning, and in what way, if at all, do recent advances in machine learning, which almost entirely the ones that we're aware of, the ones that are sort of the driver of the sort of current explosion of interest, all are primarily advances of deep learning. To what extent does deep learning actually bear on some of these broader questions? And I'll argue that it's not something we shouldn't necessarily take for granted that it does. So just some context. I think Mel already introduced it, but I'll sort of say something about what we do in my lab. Is we do sort of basic methodological research, a lot of it in deep learning. That certainly was my roots. We tend to, I guess, the reason why I maybe have some amount of contact with philosophers is just that we tend to gravitate more towards conceptual questions than to performance questions. And it doesn't mean that we punt entirely on performance questions. We're interested in building systems that work, but we're often driven by the fact that what machine learning is doing in general, what we do with machine learning is not, is often something very different in character from what we sort of claim to be doing, or certainly the sort of claims that people selling the systems claim to be doing. If you look at, what sort of drives you to say, I want to make better medical decisions or something like this, I want personalized healthcare. We look at what people actually do is say, here's something that I can call a feature, here's something that I can call a label, and let me train a model to predict Y given X. And there's a huge amount of the actual problem that gets lost in the formulation itself. So what's changed is we have better tools given the formulation. What's sort of stubbornly persistent is the gaps in the formulation itself. What's fundamentally just not even being approached by the kinds of setups. And I think in some way that there's maybe something in common about theory and application that's not shared by, say, empirical methodological work, is that in both cases, you're sort of in touch with these things. But I'm not going to elaborate. I'm going to move on just a little bit. So what are we doing with deep learning? I'll argue that basically all we're doing is curve fitting. It's not a new argument. I've probably heard Perl make a similar argument, and it requires just a grain of salt that there are some exceptions. But even to the extent that there are exceptions, like reinforcement learning, which isn't entirely curve fitting, there's an element of interaction with an environment. The part that's new, the part that makes it deep learning, is just the curve fitting part. It's that we're fitting a different family of models. So here's here you go. Deep learning made this possible. So what is curve fitting? Basically, we say we have some population of interest. I'm interested in estimating some underlying parameter, which is like a parameter of the actual distribution of data in the underlying population. It could be an infinite population, like when you have a stochastic process. It could be like a finite population just so large that you couldn't possibly encounter every single individual. And so you say, I want to estimate some parameter of interest. Now, this parameter could be really simple, like just an average. So, here's some photo, whatever, it's not a photograph from 500 years ago of people lining up to have their feet measured. So you could determine what is the average length of the foot. I think there's stories in some of like the classical like Indian epics about people. It's like Hacking has some reference to one of like using the sample average to estimate the number of leaves on a tree. We've been doing this for a long time. We're not limited to estimating simple averages. We can estimate, say, something like what are the parameters of the model that best fits, achieves lowest error on examples in this underlying population. And so you have for hundreds of years now the method of least squares. So I guess maybe one of the more famous disputes in terms of provenance of ideas between Gauss and Legendre. We're not limited to regression problems. Just estimate a real valued quantity can try to fit a classifier, try to distinguish among categories of items. And we had a sort of explosion of activity in the late 50s, early 60s that extended the tools that were sort of maybe by that point hundreds of years old in the context of regression on continuous values to classifiers. And you might be familiar with Rosenblatt's Perceptron, which is sort of a progenitor of modern deep learning. A lot of ideas in that paper. Actually, a lot of things we do in modern deep learning, including some non-obvious ones, were already happening then, like data augmentation. Logistic regression was developed right around that time. So like the logic function had existed for modeling certain things like the growth of populations in certain contexts, but actually like fitting parameters of logistic regression model to make probabilistic classifications was a new idea in about 1958, I believe. And Vapnik and Chernovenkis introduced the linear support vector machine, which is sort of a different perspective on making classifications. It's not about outputting probabilities, but rather about sort of the geometry of the data, coming up with a max margin separator. And it's not even such a new idea to say, well, what if we had really, really, really flexible models, right? We've been doing this for a long time. So non-parametric methods are sort of arbitrarily complex. They have a lot of the properties that neural networks have. They're capable of their sort of complexity of the resulting model sort of depends upon the amount of data and the complexity of the data that you actually encounter. So if you had linearly separable data and you train like a nearest neighbor model on it, what you'll get out will look something like a linear separator. But for any sufficiently smooth function, if you had enough data, You'll be able to approximate it arbitrarily well with a k-nearest neighbor model. And so we've had the idea of, we can fitting really flexible models before. So what goes wrong with these models? They require a priori someone to specify the right notion of a similarity function. Turns out that for most high-dimensional data sets, we don't know what it means for any example to be more similar to any other one. Like what makes two photographs similar? Things like just computing the distance in raw image space doesn't quite make sense. These methods also tend to explode as the amount of data gets larger. So they don't cope very well as the data set size grows. This is something where there's actually been a lot of progress recently, and it's actually a shifting landscape. Kernel methods can scale up quite a bit more than they ever could before. The basic idea here, though, what almost all of this consists of is just given a data set and some inductive assumption. You don't have any inductive assumption, you can't learn anything. Produce a mapping. And I'm saying this in a slightly generic way, just produce a mapping. I'm not saying input and labels, because it's not always that you have labels. It could be that I want to learn a density function. Still requires an inductive assumption. No one actually gives you labels and says, for this example, this is its probability, but you can infer a density with a sufficient set of inductive assumptions. But most often, I think it's fine for the cases we're talking about. You're learning a mapping from some input X to some output Y. So first, just checking in before we go too far, with like, let's get into deep learning and see, can you understand stuff? What's doing is just, what are the fundamental limitations of this setup before we kind of get lost in, the wonder of deep learning. Just fundamentally, just flowing from the way we set up these problems. If I have a fixed data set, I train a model, I'm hoping that given some examples, this is the input, this is the output, I'm going to recover some function. And what's my goal? Is just to be able to predict accurately on data that I've never seen before. When I say data I've never seen before, we don't have the ability to say this in a very strong way. What you'd like to do is what science does, maybe, is to say, oh, I'm going to make a bunch of observations on Earth, and then I'm going to infer some set of principles, and then I'm going to say, well, if these are right, then it would also be the case in these other settings that are very statistically different from anything I've ever seen before, that this is, what should happen. And then you'll go, like, when you try to falsify a scientific theory, you don't just present new data from the same distribution. The theories have a stronger sort of predictive power, a stronger sort of claim. And when you attempt to falsify them, you go out and you run new experiments where if this theory were right, then in this new setting, in this new distribution of data generated from some new intervention, this is what I should expect to see. And you only kind of accept the theory as useful or even as predictive when it sort of performs well despite this. This is not the thing that we achieve with any of these curve fitting methods. What we achieve is we do well in precisely the distribution which we've trained. And insofar as there's any kind of ability to go beyond that, it's with respect to some very specifically specified invariance, like your prediction should be insensitive to a certain kind of perturbation. Sometimes we can build that into the modeling. Even that, we suck at it. So we've had tens of thousands of people writing hundreds of thousands of papers just to deal with like the very simplest, most goofy notion, which is just that your prediction should not change too much if the input moves a little bit. Very literally a little bit, meaning L2 distance and input space. Even that, we're not good at it. So we just learned mappings. There's no concept here about measurement. What is it that the data represents? That's not what we do. That's not what the technology does. So any sort of connection, any kind of binding between the model and the world that's supposed to represent, the conclusions you could draw, what actions you should take in that world, in any kind of actual ML system that anyone's using, that work is all done by duct tape and silly putty. It's all heuristic. Somebody making a decision of, maybe, given that I know what this data is, I have a speculation that if I can train a model on data collected in such a way and it's able to predict this thing kind of accurately, maybe if whatever this prediction looks like this, I do this action. Whenever it looks like that, I do that. Maybe that'll do something that I want in the world. The model has no concept of the fact that there's a world. It's not a thing that models do, right? So when you have, you're at Amazon, or you're some company, we had a conversation somewhere earlier about recommendation systems. The people building the recommendation system doesn't even know what a recommendation is. It doesn't have a theory of it. All it is just says something like, let's train a predictive model to predict what people are going to purchase given what they have purchased, or something like that. And someone says, maybe if we then take those items that someone hasn't yet viewed but are predicted to be likely to purchase and put those as the ones that they see in the recommendation carousel, maybe that will be something that will lead people to buy more things. It's total speculation. And the actual work of deciding that that's the thing to do, it's the thing that the human data scientist does. And the work of validating it is that's the work that, again, it's a bunch of people sitting around doing it. So all the model's doing is the part that's running the curve. At the same time, curve fitting is not something to be sneezed at. It's difficult. There's a reason why, many, many really good scientists have spent a long time trying to fit curves. And curve fitting, if you could do it well, gives you a whole set of tools that might not even be obvious. Like it might not be obvious that certain problems could be reduced to curve fitting problems. So this is where we get to deep learning. What is deep learning? How does it change things? Well, deep learning changes the kinds of data that we can work with. So I said kernel methods, general, before we had let's use super high bias, low variance models, or let's go into the world of really flexible non-parametrics. But on the other hand, models that we had before they broke down when our data was high dimensional because we didn't have the right similarity function. They required this to be sort of baked into them. They broke down when we had large amounts of data for computational reasons. Deep learning scales really nicely with the amount of data. So it's not like you don't have some kind of fundamental dependence that if you double the size of your data set, it'll take 8 times as long to run your algorithm. It doesn't happen. It changes the shape of the data we can work with. Now, the fact that deep learning, why is it that deep learning can deal with super high dimensional data? And we somehow seem to escape the curse of dimensionality. We're actually able to get accurate predictive models. The short answer is nobody knows. There's no great theory. We don't have an analytic characterization of the inductive biases of neural networks. There's a lot of attempts to theorize about neural networks. And there's even, I have some colleagues who are doing great work, but it's important to understand that this is in its infancy. The theory has almost no explanatory power. Deep learning, the theory of deep learning has almost never made a sort of prospective prediction. It's never said, oh, here's some property that the theory says a neural network should have, and then we go and find that they have it. It's almost always retrofitted, where you're basically engineering a set of assumptions, what assumptions could I possibly make, and what analysis could I do such that I might observe what we actually already know is happening in reality. And sometimes you can get a theory that can sort of give you a stylized explanation of why what's going on might be going on. The honest answer is nobody knows what's going on. What we know is that when we train these models on datasets, we're actually able to get good predictive models, even when the data is so high dimensional that we think we have no sort of theory that says we should be able to make accurate predictions with so little data in such high dimensional settings. So we're able to tackle different kinds of data, high dimensional data. We have a sort of new family of inductive biases that we don't know how to describe analytically, but we sort of, we're good at producing people who can they have the right set of Lego blocks that they can explore the space of ways of tweaking what the model, finds easier or harder to learn. And we're able to learn mappings from very different kinds of objects. So we could take a lot of problems and turn them into prediction problems that might not be obvious that they're prediction problems. So if you're used to thinking about prediction, thinking about classification, regression, but we can learn things like predict a sentence, given a sentence. That's how modern translation systems work. It's still just curve fitting. It's still limited. It's got a sort of very limited epistemic window by what is represented in the data set, or what is likely, were we to think of, what is sort of likely in the distribution, implied by the data set that we have. There's certain kinds of queries that we fundamentally can't answer because they're just not associational queries. It doesn't resolve normative disputes. It doesn't have any sort of normative reasoning power. The neural network doesn't answer counterfactual or causal queries. It's fundamentally incapable, not because you couldn't use neural networks in a causal reasoning system to attack a causal question, but just because the only part that deep learning changes is what sorts of curves we can fit. So if at the end of the day, it's impossible to infer something from observational data alone, then it's impossible to infer that thing from observational data alone, regardless of what model you feed that data into. I think we can lose sight of this once we start getting lost in the like, oh, GPT said whatever. Now, something that's important to keep track of with deep learning is deep learning relies really heavily on the train test paradigm. We have, even just to say, is it working well in any sense, we only can say that it's working well on sort of the population from which we have samples to evaluate it. So with some kinds of models, with a linear model, on enough data, you have this sort of like high bias, low variance setting, and you could say, well, no, it might still be a somewhat loose guarantee, but it'll be a non-vacuous one. I could say that, okay, given some data, I can be sure that if I'm able to, however well I'm able to fit the training data, it's kind of similar to how well I'm able to fit unseen data from that same population. With the deep neural network, you can't say anything like that a priori. So what we have is a set of practices where you say, well, you know what, let's forget about that. Let's train a model, fit the data as well as we can, and then check and see how well we performed. Now, there's issues about like hammering the same test sets over and over again, but at least there we're not fitting our parameters. We're not fitting infinite hypothesis classes on the test set. We're coming with people's best models, and so you can handle millions of individual hypotheses and do reasonably well. So for sufficiently large tests, it does really well. The other thing that where deep learning kind of like leaves us stranded is when we don't have a test set. When we try to answer any sort of query where the answer isn't directly observable. And so I think people get confused or lose sight of questions of identification. Deep learning, our only sort of certificate, our only sort of confidence comes from the fact that we evaluated on some test set for which we knew the answer. There've been a lot of breakthroughs. Convolutional neural networks can make accurate predictions of what class applies to an image. They can identify bounding boxes around specific objects in images. They can segment images where you have a per pixel classification for what sort of object category they belong to. And far better than anything we've ever actually been able to get to work before. Again, as assessed on sort of independent samples from the same distribution from which, the training data was gathered. Now, in reality, what happens when we go out into the world? Sort of all bets are off. Now, there are some, it doesn't necessarily mean that your model will always fail the instant that your data is in any way non-representative. It means that you have sort of no basis for expecting how it'll behave. Now, obviously, if you train a speech recognition system on 10 billion hours of human speech taken from every single person's phone, like all over the entire world, and then you just pick a random person, and maybe it wasn't like you did a true IID draw from their population, there's like a good chance your system's going to work well for them. And that's kind of the world we're in. But all kinds of other changes could totally mess up models. They don't anticipate what's going to happen if like your prediction is actually used to drive a decision, which controls a set of incentives to which people are going to respond. This is all like a kind of structure that has nothing to do with deep learning. Deep learning isn't aware of it. Deep learning doesn't handle it. We can plug deep learning into some kind of more structured, setup where maybe it can handle the pattern recognition part, and we can have some other kind of reasoning that's operating at the meta level to deal with the structure of, say, incentive effects or distribution shifts. And that's a lot of what we do in lab. There's a lot of things that are not obviously curve-fitting problems, but can be cast as them. So, it's obvious that like predict a label given an input is a curve-fitting problem. Less obvious as saying, oh, here's a bunch of images. Now I want to be able to sample images that look as though they were drawn from the same underlying distribution. It turns out you can sort of like turn this into like two curve-fitting problems and try to solve them both simultaneously, right? Have one model whose job is just to predict, is this a real image or is this a fake image? And another one to try to output models that are hard to distinguish, where basically you've turned the first model into an objective function to the second model. But again, it's cool in the sense of we have this weird set of capabilities. It's not obvious if you're sitting around like you were familiar with the state of statistical learning up through like the 1960s, and then you went to sleep and you woke up today and you said, oh, this neural network could generate, like whatever, hallucinate I think we have to be careful with the anthropomorphic language, but like if someone told you a neural network could somehow just conjure an image that looks like a high resolution photograph, well, probably if you went to sleep in 1960, you wouldn't even know what a high resolution photograph was. But then once you make use of that, it would not be immediately obvious that this flows directly from the same set of principles as, training a classifier. We're able to make predictions based on raw text. Even when I started my PhD 8 years ago, 9 years ago, 8.5 years ago, we didn't handle raw text. The state-of-the-art ways for making classifications based on text were basically take your vocabulary and count up how many times does the word A appear, how many times the word, banana appear, how many times the word whatever. Just count how many times each word appears, and that becomes your representation of the document. Completely discard word order. Now we have much, much better models that you have a flexible neural network to handle variable size input. We're able to also handle variable size output. And what we do is we basically break down your output into a chain of tokens. So you want to predict a sentence, what you say is predict what's the first word in the sentence going to be. Okay, given whatever you predicted and the input, predict what the second word is going to be. Okay, now add that to the conditioning set, predict what the third word would be. And that's how all machine translation systems work. This is all that they do. And so the question is like, are we just getting better at prediction, or are we actually even tickling any problem that goes beyond just statistical prediction? And the answer is like, I don't want to be too dismissive, because the answer is there are some, in some sense, what we are doing is just statistical prediction, but then there's also some of this important ways to take stock of how the landscape has shifted in some interesting ways. One is that neural networks give us this kind of weird window into how different tasks are related to each other that doesn't quite have an analog in the classical world. And one of them is, for example, this preoccupation with large language models. The large language model, it's just this. This is all it is. It might be operating on word pieces, which are like something between a character and a word, not on characters, but it's the same idea. It's just basically, you have a model with some kind of memory. It's basically able to look back at some amount of context, typically something around like 1,000 tokens, and just predict the next character, predict the next token in the stream. Okay, now advance the cursor, predict the next token in the stream. This is all that's going on in a large language model. It's just a predictive model. It's just a curve fitting model where the curve is basically you fed in all the data you found on the internet or something, and you just always try to predict the next token given the most recent 1,000. Where things get kind of interesting is that you could take this model and instrument it in ways that are maybe not obvious. Like you can engineer a set of prompts such that, you could say, I've never trained this model explicitly to perform sentiment analysis, but what I could do is I could just feed in a document, and then I could say, write the sentence, the prefix, like the sentiment of this document is, and then just look and say, is the probability higher for positive or for negative? So you're able to exploit the fact that like somehow just curve fitting on some enormous data set could somehow give you, with some clever way of instrumenting the resulting model, the ability to solve a bunch of other tasks that weren't what you explicitly trained for. And these facts were even recognized sort of after the fact. People were just focusing on, oh, it generates text that looks kind of real-ish, whatever that means. It looks kind of coherent. Again, a large language model, it doesn't understand anything. It doesn't know what the text refers to. All it has is the ability to estimate a conditional probability of a word given its context. It doesn't use language intentionally, right? The model has no notion of what could be accomplished with language. It's very different. I think there's something about the way you get lost when you look at these images. When people start talking about like neural network art, it's not art. But importantly, it's not art because there's no intention. The goal of an artist isn't to be confused for someone who might be making art. You have to have a point. When you make an argument, it's not, I just want like someone to think that I'm a human up here talking. I have a specific thing that I want to get across to you. Like there's a kind of like normative agency in being a human that is completely missing from all these systems. So all it is an estimate of a conditional probability, but that's not something to be completely sneezed at. Again, right? It doesn't know what's contained in. All it knows is what's contained in or likely given the data. Anything that's fundamentally unidentifiable from the data is not going to be identifiable by the model, right? It doesn't engage in normative, it doesn't engage in causal reasoning, not by itself, although you could, what causal reasoning does is it gives you a way of turning causal queries into predictive queries. And now there's nothing to stop you from using the deep learning or whatever function approximator you want to handle the predictive part. Neural networks reveal sort of shared structure among different things that we want to do that's sometimes surprising. If you want to train a linear model to predict one thing, and then you want to train a linear model to predict something else, you just train from scratch every single time. Neural networks learn multiple layers of representation. It turns out sometimes when you share the representation layers among many different tasks, even if each one has a relatively small amount of data, sort of each task forms like a sort of useful inductive bias for the other, such that by learning a shared representation, you could do better on all the tasks than if you trained on them separately. It turns out if you pre-train a model on one enormous data set and then fine-tune on a somehow related data set, you tend to do much better than if you train from scratch. Why? Answer is no one's quite sure. Somehow the initialization is better. What we know is what, not why. And that's a complicated story that we have some work with, but I'll let it go. Now, at the same time, look, you do have some weird things that are, there's no denying that there are some, and this may be something that we didn't have with a lot of classical models, maybe have with like PCA or something to a lesser degree, but there are weird, like a linear model doesn't give you that much to poke around with. You don't say, let me peer inside it, or let me tinker with it, or let me turn it upside down, or fold it inside out. There's something weird about neural networks that, people have found, let me take a model that's trained just to classify images, and then now I want to take an image and try to find another image that's close to the original image, but such that it excites a particular neuron in some other network. And they come up with all kinds of ad hoc ways of using the models that don't correspond directly to any kind of predictive task. Unclear why the property they're looking for should fall out of the fact that you just trained a predictive model, but you can get all kinds of weird things. You can get, a neural network that turns people's faces into dog faces, or you get, so there's something going on in the network that produces, sort of weird, sort of emergent side effects that people are captivated by. There's another way deep learning kind of bears on the landscape, which is this question of, even if all that deep learning does is function approximation, function approximation is like an important subroutine, right? Fitting curves, like neural networks don't solve causal inference, neural networks don't solve reinforcement learning, but part of whatever algorithm used to solve reinforcement learning needs to learn a mapping from states to actions. And if it turns out that neural networks are good at learning mappings, we could replace whatever we used to use to learn the mapping with a neural network. In my own research, we tackle problems of distribution shift. And here the question, I'll just summarize like 1 minute, is basically we want models that will predict well, not just in the environment on which we trained, or in the distribution from which our training data was sampled, but some other distribution. The problem is that we live in that world again, the deep learning world, where deep learning business as usual sort of, normally all we get is the certificate we get from evaluating on the test set. And the future environment that you might encounter, sort of the normal setup is you don't get a test set from it. You don't get labeled data from it. So what can you do? And one kind of useful tool that we've used over and over again is to, we want to be able to estimate something like the best predictor in some new data set that's related in some, say, known way even to the train set. We want to use deep neural networks to do it, but we don't have a test set for the holdout data. So what can we do? And one move that we've been able to make is to say that sometimes prediction implies more than prediction, or at least in-domain prediction coupled with the right set of assumptions actually does imply the capability of out-of-domain distribution. And I'm happy to talk more about the details, but the high-level idea is that sometimes if we make the right sort of set of structural assumptions on how the environment can change, we can fashion an IID prediction problem such that if you can solve that problem and produce a classifier that's good, not like in a sense of like it's perfect, not that it's Bayes optimal, not that it's perfectly calibrated, but just for some mild notion of good. Like it's got a non-degenerate confusion matrix. When it makes really confident predictions, it's kind of right much of the time. that then you can use this black box model as an instrument to identify whatever it is that you're looking for. What is the parameter of interest on the target distribution that was related through some known family of possible changes that your environment could go through? So there are ways to get deep learning to be useful, at least as a sort of like subcomponent or subroutine as part of a much larger system. But at the same time, I think there's a bit of a tendency for us to ascribe all sorts of faculties and agency to these models that just fundamentally isn't there. So I'm really looking forward, to meeting everybody and exchanging ideas. And thanks for indulging me.
Is this on? How about now? All right, we're moving on to a couple of quick questions. Does anyone have a question?
Good afternoon, Dr. Lipton. I have a question regarding the large language model. So most of the language models that are say training these days are only say based on training on the training objective of the next word, like evaluation for data handling objective of the next expression and mass language modeling. So my question is, are there any new objectives that have say come up by say training a larger language model? And also the follow-up question on that is, did you see the recent down model from OpenAI which generates images?
Sure.
So that model is actually say generating images based on living caption. So say if you get it to generate a model for say and have a category or you generate a category. So would you categorize that language model as say it is actually understanding language?
No. The first question is about generally large language models. So in general, there's one main objective. So one weakness of having a large and expanding community and not having a sort of a review process that involves the possibility of revisions is that if a paper is interesting and sort of like in spots painfully like misleading or abuses or overloads notation, it slips through. And one unfortunate slip is that we use the word language model to describe sort of any sort of pre-training objective based on text, and it's a misnomer. A language model is just a density function, or I should say, if you want to be really proper, like a probability mass function over sequences. And so a model that's trained to predict the next word truly is a language model, predicting the next token, because you can assign, basically by like the product world rule of probability, you can assign a probability to any sequence by multiplying together the conditionals, right, of each, consequent given the entire prefix up till that point. What we call, like, BERT is not a language model. A math language model is just not a language model. What it is it fits broadly into this sort of like repertoire of techniques called, some people call it self-supervised learning, but the sense is that basically you just conjure up you don't actually have a task that you care about. What you do is you say, I've got an enormous amount of data. Is there some task that I can like invent, some artificial task, such that if I train in that way, and then subsequently fine-tune on the task that I care about, for which I have labels I do well. And so basically, all that we know for the most part is what kind of seems to work. And mass language model, what it does is it says, I'm going to take 15% of words or whatever, I'm going to blank them out of the input, and then I'm going to train the model to basically just fill in the blanks. Then other people say, I'm going to feed in the model, and you're going to try to predict what's the subsequent sentence in the corpus. And people come up with a million different ones of these. I think for the most part, it's one of these things, it's kind of like architecture engineering. Why do we use one architecture and not another for computer vision? At the end of the day, really just because people seem to be getting better performance. And so people are exploring, but they're not exploring, the sort of like alchemy metaphor is like a little bit played out maybe, but there is something fundamentally alchemical in that there is no guiding principle. There is no theory that says if this is your objective, you'll do better. What's happening is basically people say, I'm going to predict some part of the input from the other. And they'll twiddle with how long is the passage that you feed in. Do I mask things out? Even after I mask things out, do I penalize the model only for its prediction on the mask or for the other tokens? But this is mostly, I think, this is just like the world of fiddling. And I think we'll see something kind of similar to what happened with model architectures for computer vision. 2011, what was the state-of-the-art model for image classification? Who knows? 2012, AlexNet. 2013, VGG. 2013 and a half, like VGG with batch normalization. 6 months later, ResNet. If you were right now, I would hand you a data set and you wanted to go classify images. Somewhere in the middle was, what was it, like the Google Net or whatever. But anyway, if you were right now in 2022, what's the best model? The best sort of like off-the-shelf default for classifying images? Still ResNet. So, it's a world of kind of fiddling where there hasn't really been a fundamental advance. We discovered a few knobs, and it took people a while to tune them, but it's kind of like tuning the regularization strength. You get gains until you don't. In terms of DALL-E, I think I don't understand the impulse to use the word understanding. Like, I think it's really just a rhetorical move. I don't think it carries any more weight than that. We say, does a model really understand? Because why is it any more really understanding to conjure an image given a prompt that, given text, than to conjure the text given the image?
Any more audience questions?
I'm in the audience. I can take one more break. Certainly appreciate the recommended cold shower for certain people getting really over heels and heads on what deep learning really up to, somewhat familiar with the details. I wonder though, just a mild pushback. I can imagine someone at some point saying, well, I've looked at the brain. What's going on there are just lots of neurons firing. That's it. Brain doesn't understand anything. This is old philosophical debate. Brain doesn't have an intention. Brain doesn't understand anything. So, it's too bad. We have these brains that do lots of things, but they don't do anything that humans do. Well, of course, somehow all that neural firing, most people's view, does add up to having attention to really understanding and so on. And so, there are lots of things that currently can't be scaled up to do that are somewhat surprising to your mentioning. Maybe some of the enthusiasm for people who see, such human-like abilities may act on some of the thought that, boy, they're doing what seems like the hardest part of what we do. So maybe it doesn't intend to do anything, but intention, that's not going to be too hard to explain or to give a system. And then understanding is just going to be something that we say on a system when it accomplishes this or that. The GPT-3 writes better essays than some students out there, who seem to understand the content at least somewhat. So, so is there a kind of categorical difference? And maybe you spoke this, and not clear in my head, but something where you say that, like, look, understanding requires this, and I guess you're getting beyond curve fitting. I guess maybe what they highlight is like, here's something humans do on a regular basis. It cannot possibly be seen as curve. Yeah, a couple examples of that.
There's a lot of things. I guess think where to begin. So one is I think that sort of like I looked at the brain and is just somewhere if I go deep enough, maybe I just look at the atoms, maybe I just look at the whatever. You say there's just something mechanical happening. I think this is sort of like I don't think you're truly just. I think you're setting up an argument for debate. I think not necessarily like putting your force behind. So I think I'm within rights to push back. I guess it's kind of like in some ways like the sort of straw man that like Hofstadter sees in Searle or something. This sort of like you know, like the thing that matters is like if I zoom in enough, like if I built a computer out of Coke cans, is that different than if I build it out of transistors versus I build it out of, you know, organic matter? I think it's the wrong level, or the thing of like, I don't know, like if I zoom in close enough, like I want to look at the economy, but if I zoom in, like where is the economy particle? Like it doesn't exist. It's, and then I think like everything that is interesting that there is talk about, I think anyone, so I'm saying look at Maria because she knows a lot more about the state of neuroscience and a lot more about the brain than I do. But I think every neuroscientist I've met that, you know, has an ounce of sobriety is quite modest about what, if anything, we can claim to really understand about how the brain is organized or what the hell's going on there beyond, you know, I think our resolution really increases a lot. Like the more we zoom in, I think we actually understand quite a lot about, say, like what causes an individual neuron to fire an action potential or something like that. I think it's something where like we understand things mechanically. But I don't think we understand learning algorithms. I don't think we understand the formation of. So what are things humans can do that models don't? Among other things is to design tasks, to decide what to do, to have some awareness of the epistemic boundaries between like what you know and the world that you live in, and to say have this to take sort of to have design experiments, to attempt to falsify them, to ultimately have some kind of machinery that could develop extrapolative principles. Like we went to the moon successfully the first time. You know, like imagine doing this with supervised learning. Go to the moon and do it 1 million times under 1 billion different conditions and record every single thing you do and train a predictive model to predict what the human astronaut would do or something. It doesn't quite add up. Well, let's do it with reinforcement learning. Let's put a reward on the moon. You get to the moon, you get the reward. In fact, you know, reinforcement learning systems today don't even quite recognize, for example, you know, things like you train it to play Pong and then you change the size of the paddle. And that, okay, you know, you sort of like wind up like falling back to the level of random guessing. Now, I think that's the level, I think it's a little bit of a straw man. I think that's the kind of thing that is potentially surmountable within our machinery. It's certainly more approachable than like, how would you get an automated system that was sort of like earthbound to come up with a way of getting to the moon. We're just sort of starting from that, that's your goal, get to the moon. And to say, okay, well, here's potentially a set of composable primitives that would get us there. Forming concepts, like actually concepts like systems of understanding what are like, you know, in the sense that the sciences do, you know, some notion of this is the fundamentals, not because just these are examples that happen to clump together in the feature space, but actually to like develop concepts in the sense that the natural sciences do, even if we don't have like, you know, can't spell out the exact algorithm for how we do it, but this process of sort of reevaluating your sort of system of what sort of entities you think exist in the world and what are the relations among them. These are things that we're not even tickling with the category of methods. And it's not to say like I'm not like a, you know, I'm not like whatever it is, like I'm not a religious person. I'm not like oh, like things can only happen in meat and they can never happen in silico. This is more specifically targeted at the capabilities of the sort of like current, if I can misuse the word paradigm, technology. Yeah.
Very much on the side of Zachary in terms of, I think what he's doing is very important in terms of cutting down some of the around what people understand. But the problem is the word understand. You guys should be defining it better. Because you don't define it, we are stuck with a Gödelian thought that both the following statements are true. AI systems don't understand, it's true. And any test you can possibly make to show that AI systems don't understand, AI systems will pass. That's what is happening in random things like ethics and random things like the Vinograd paradoxes and so on and so forth. It's, even after things that he's tackling about concepts and so on, there would be things that people actually show that systems are able to generate them. And so I think the word understand is just way too loaded that eventually I agree with the fact that, I think there is something that is said in one of the slides that things that even LLMs are can tell you when they come up with things that we are surprised in, it's oftentimes they are within the distributional closure. Just because it's in the distributional closure doesn't mean we understand that they are there. So we are surprised. So same thing, deductive closure. Chess is a deductively closed game, and yet we can be surprised at the move that somebody made that we have figured this out. So I think oftentimes people confuse that. You can't stop people from being impressed at what they're interested in. If they are impressed at what LLM said, that's fine. But exactly, it's right that it's within the likelihood, that it's generated. It's not exactly like that's what you see, but it's.
And sometimes, you take any complex system that you can monkey with. Sometimes you find a way to monkey with it such that something cool comes out of it. It doesn't mean that, it doesn't mean that it is doing the I don't know, like you spill epoxy and like a bunch of pigment into it. It makes cool patterns, and it's not because it has any kind of cognitive faculty. It's just that you kick the system in a way, and you found what happened interesting. Yeah, I think what you said about understanding, I think that this is our role is, I think this is where ML, by losing, it's a great thing about the community. It's the thing that we've enjoyed, that we have such low gates to entry. It's been beneficial in a lot of ways. It's allowed a lot of stuff that was I think a lot of more mature communities wouldn't have allowed to happen to take root here, that turned out to actually work and be interesting. The downside is we're very undisciplined in that we don't write I say we, I think the median ML paper does not have the standards for scientific writing that say it's not they're not coming out of the school of Claude Shannon or something. It's not how they're writing. And I think the danger is a technical claim needs to be technical. And I think it's totally fine to put over paper and say, here, this thing looks cool and something's really interesting. And even to speculate. But I think the dangerous thing is when understanding or fairness or any of these things get very naively just attached to you make the form of the technical claim to appear to be bearing upon the right when we both agree that understanding's perhaps vaguely defined, but given that it's vaguely defined, it means that we can't make a technical assertion about it, right? And so I think the scary thing is that you read the papers and they do. Yeah, I think this gets propagated and it circulates, and then philosophers think we've actually done something we haven't done, and the media thinks we've done something we haven't done.
Maybe artificial intelligence as a science is allowing us to progress to fitness or concept of understanding.
Maybe.
Well,
Let's thank our speaker once again. Let's hear from Mariah.
I'll introduce you.